In a solid, the constituent particles, atoms, ions, or molecules are closely packed. Hence, they possess rigidity and have a definite volume and a definite shape. In gases, the molecules are completely free to move about, therefore, they have neither a definite shape nor a definite volume. They fill up the whole vessel of any volume and also take up the shape of that vessel. However, in a liquid, the molecules are not fixed as in a solid, and at the same time, they have some freedom of motion, though they are not as free to move as in the case of gases. Thus, they show a behavior in between that of gases and that of a solids. Like solids, they have a definite volume, whereas unlike solids, but like gases, they do not have a definite shape. They take up the shape of the vessel in which they are put. This is expressed by saying that liquid state is an intermediate between gaseous and solid state. As explained above, the differences in the behavior of the three states of matter is mainly due to the intermolecular distances of separation. In a solid, the constituent particles are closely packed, almost touching each other, and may be treated as hard spheres. In a liquid, the molecules are separated by small distances of the order of molecular diameters, while in a gases, the intermolecular distances are so large that the molecules can move even randomly within the vessel. The arrangement of particles of the three states of matter in the two-dimensional space may be represented as follows. See figure 2.1. These intermolecular distances suggest that the cohesive forces or the intermolecular forces of attraction in a solid are very strong, whereas in a case of gases, they are very weak, and in a case of liquids, they are in between. That is, they are fairly strong to keep them in the condensed state, but not strong enough to hold them in the fixed positions, as in a solid. In fact, all the characteristic properties of liquids, such as vapor pressure, surface tension, viscosity, etc., as will be discussed later in this unit, arise due to the nature of intermolecular forces existing in the liquids. 2.2 Intermolecular forces or van der Waals forces. The forces of attraction existing among the molecules of a substance, gaseous, liquid, or solid, are called intermolecular forces or cohesive forces. These forces are of three different types as explained below. First come to the dipole-dipole attractions. These forces of attraction occur among the polar molecules. The reason for the origin of these forces is quite obvious. Polar molecules have permanent dipoles. The positive dipole of one molecule is thus attracted by the negative pole of the other molecule. A simple example is that of HCl, in which the chlorine, being more electronegative, acquires a slight negative charge, whereas the hydrogen and becomes slightly positively charged. The dipole-dipole attractions then take place among the HCl molecules, as shown in the figure 2.2. Proof for the existence of dipole-dipole forces. If dipole-dipole forces exist among the polar molecules, they should have higher melting points and boiling points than the non-polar molecules, provided all other factors like molecular mass, molecular shape, etc. are the same. This is actually found to be so. For example, the non-polar molecules N2, nitrogen, and oxygen have boiling points minus 196 degrees Celsius and minus 183 degrees Celsius respectively, whereas nitric oxide NO, which is slightly polar, has a higher boiling point, namely 1 point minus 151 degree. Magnitude of dipole-dipole forces. As the charges at the ends of the polar molecules are not as great as the charges on the ions in an ionic compound, the magnitude of dipole-dipole forces is therefore much smaller in comparison to ion-ion attractions or ion-dipole attractions. Further, whereas the force of attraction between two ions is directly proportional to 1 upon r square, the force of attraction between two dipoles is proportional to 1 upon r ki power 7, whereas r is the distance between the ions in the former case and that between the dipoles in the latter case. Consequently, under similar conditions of temperature and pressure, Since the intermolecular distances are very large, the dipole-dipole forces of a temperature and pressure, dipole-dipole forces of attraction among the gaseous molecules are very small. As the pressure is increased or the temperature is decreased, the distance among the molecules decreases, that is, the molecules come closer. As a result, the intermolecular forces of attraction increase and the gas changes into a liquid or a solid. The magnitude of dipole-dipole forces in different polar molecules can be predicted on the basis of the polarity of the molecules, which in turn depends upon the electronegativities of the atoms present in the molecules and the geometry of the molecules. In case of polyatomic molecules containing more than two atoms in a molecule, the polarities of the molecules are usually expressed in terms of dipole moments of the molecules, for example, comparing the molecules of NH3, ammonia, and H2O water. The dipole moments are 1.49 d and 1.85 d respectively. Thus, though both have nearly the same molecular mass, the intermolecular forces of attraction are stronger in case of H2O than those in the ammonia. Consequently, H2O has higher melting point and boiling point than those of NH3. In fact, it is well known fact that whereas H2O is a liquid, NH3 is a gas. Hydrogen bonding. It is a special case of dipole-dipole attractions. It occurs in molecules containing a hydrogen atom linked by a covalent bond to a highly electronegative atom but small in size, that is fluorine, oxygen, nitrogen. Because of the large electronegativity difference between the hydrogen atom and the highly electronegative atom, the hydrogen atom acquires a slightly delta positive charge and the electronegative atom requires a significant delta negative charge. The positive end of the one molecule then attracts the negative electronegative atom of the other molecule. For example, the cases of HF, H2O, and H3 may be represented as shown below. Because of the great polarity of these molecules, the intermolecular forces of attraction are stronger than the ordinary dipole-dipole attractions. That is why this type of intermolecular attraction is considered as a bond rather than mere dipole-dipole attraction. This type of bond is called hydrogen bond and is represented by dotted lines as shown in the examples given above. To sum up, hydrogen bonded may be defined as the attraction of hydrogen atom of one molecule by the electronegative atom of the other molecule. In case of compound containing a hydrogen atom linked to a highly electronegative atom but small in size. Further, as shown above, in each case the hydrogen atom is linked to two electronegative atoms simultaneously, one by a covalent bond and the other by a hydrogen bond. Thus, hydrogen acts as a bridge between the two electronegative atoms. This is sometimes referred to as hydrogen bridge. Strength of hydrogen bond. As mentioned above, hydrogen bond is stronger than ordinary dipole-dipole attraction. However, it is much weaker than the covalent bond. The energy of the hydrogen bond lies between 20 to 40 kilojoule per mole, whereas that of a covalent bond is usually between 1.60 to 600 kilojoule per mole. Depending upon the electronegative of atom, the strength of hydrogen bond follows the order HF, then H2O, then ammonia. Second, dipole-induced dipole attractions. The positive end of a polar molecule may attract the electron cloud of a non-polar molecule lying close to it, thereby polarizing it. Thus, the non-polar molecules becomes an induced dipole, just as it happens in case an iron piece is brought close to a magnet. As a result, the attraction takes place between the polar molecule, that is a permanent dipole, and the non-polar molecule, that is an induced dipole. 3. Induced dipole, induced dipole attractions. London forces or dispersive forces. It is easy to conceive ion-ion attractions, ion dipole attractions, and ion dipole attractions. However, the next very significant question is what intermolecular forces attract non-polar molecules to each other in the liquid and the solid state. The origin of these forces was proposed by Fritz London in 1930, hence they are termed as London forces. These forces are thought to arise from the motion of the electrons. It is believed that at any instant of time the electron clouds of the molecule may be distorted so that a momentary dipole, or that there is a dipole for a short while, is produced in which one part of the molecule is slightly more negative than the rest. The momentary dipoles induce dipole in the neighboring molecules. These are then attracted to each other exactly in the same way as the permanent dipoles. The forces of attraction between the induced momentary dipoles are called London dispersion forces. It may be pointed out that since all molecules contain electrons, London forces also exist in the polar molecules. However, in case of non-polar molecular substances, London forces are the only intermolecular forces that exist. Magnitude of the London forces. London forces are the weakest intermolecular forces. Their magnitude depend upon the following two factors. First is the complexity of the molecules. Larger or more complex are the molecules, greater is the magnitude of London forces. This is obviously due to the fact that the large electron clouds are easily distorted or polarized. Since the larger molecular size amounts to larger molecular mass, it is often suggested that the magnitude of London forces increases with increasing molecular mass. Second, the geometry of the molecules. The shape of the molecules has a significant effect on the magnitude of London forces. For example, N-pentane and neopentane have the same molecular formula, that is C5H12. Yet, the boiling point of N-pentane is about 27 degrees Celsius higher than that of a neopentane. The difference can be attributed to the different shape of the two molecules, that is, the N-pentane being a zigzag chain, whereas neopentane is nearly spherical. The overall attraction between the molecules is greater in the case of N-pentane because there are more sites of attraction. The molecules are able to come in close with the entire length of the molecule. Quite often, London forces are referred to as van der Waals forces. However, it is incorrect to call London forces alone as the van der Waals forces. In fact, van der Waals forces is a general term which implies all types of intermolecular forces. It is interesting to mention here that based on the nature of intermolecular forces, cohesive forces, the liquids are classified into the following types: ionic liquids such as molten salts, metallic liquids consisting of ions and mobile electrons, liquids such as water in which molecules are held together mainly by hydrogen bonds, molecular liquids in which the molecules are held together by van der Waals forces, which include interaction between permanent dipoles, permanent dipole, and an induced dipole, induced dipole, or London dispersion forces. Mathematical treatment of intermolecular forces. Let us consider the interactions between a pair of molecules. When the molecules comes closer, there are forces of attraction and forces of repulsion between them. Experimental and theoretical studies both show that the attractive forces between a pair of molecules vary inversely as the seventh power of the intermolecular distance between them, that is Fa is equal to minus Ka 1 upon r ki power 7. Negative sign has been used because force is a vector quantity, and if we take the center of one molecule as the origin with r is equal to 0, the force of attraction is in a direction opposite to the vector from r is equal to 0 to the second molecule, that is molecule 1, from molecule 1 to molecule 2, and from molecule 2 to molecule 1, being molecule 1 at r is equal to 0. These forces are of considerable magnitude when the intermolecular distances are of the order of little more than the molecular diameter, as in a case of liquids. At very short distances of approach, repulsive forces become applicable between the molecules little more than the molecular diameter, as in a case of liquids. At very short distances of approach, repulsive forces become applicable between the molecules, but these are generally of small order in solids because the intermolecular distances are somewhat greater. It is found that these repulsive forces vary inversely as 13th power of the intermolecular distances, that is Fr is equal to Kr upon 1 ki power 1 upon r ki power 13. The net intermolecular force between the pair of molecules is sum of the attractive and repulsive forces, that is F is equal to Fa plus Fr is equal to minus Ka upon r sven plus Kr upon r 13. Instead of forces, it is generally more convenient to study their corresponding intermolecular potential energies. Potential energy is the amount of work done in bringing one molecule from infinity to a distance r from the other molecule, that is V is equal to minus integration infinity to r FDR, negative sign is due to energy released, is equal to minus of integration infinity to r minus k a upon r7 plus minus k r upon r13 into dr is equal to k r upon 12 r की power 12 minus k a upon 6 r की power 6. A plot of potential energy due to attractive forces, repulsive forces, and the net forces versus intermolecular distance is given in figure 2.6. Equation 4 is generally written in the form V is equal to 4 epsilon r naught upon r whole की power 12 minus r naught upon r whole की power 6, where epsilon is equal to depth of the well, r naught is equal to intermolecular distance when V is equal to 0. The potential as given by the above equation is called Lennard-Jones 6 to 12 potential after the name of an English physicist who made these studies. 2.3 Structure of liquids. To study the structure of a liquid means to find out how constituent particles are arranged within the liquid. The following different studies have been proposed and studies help in to know about the structure of liquids. First study will be the volume changes on fusion and vaporization. When a pure solid melts, the increase in volume is only about 1.1%, which is much smaller than increase in volume which takes place when the liquid changes into vapor at the boiling point, which is about 100 to 1000 times. Knowing that in a solid, the constituent particles are arranged in a perfect order, the small increase in volume on melting shows that some disorder has been introduced, but large change in the volume from liquid to vapor state reveals that disorder from liquid to gaseous state is very large. Hence, we conclude that the constituent particles of a liquid are not as ordered as that in a solid, but at the same time, they are not as disordered as that in a gas. Second theory will be the enthalpy of fusions and vaporization. The amount of heat required to melt 1 mole of a pure solid at the melting point, called molar enthalpy of fusion, delta HF naught, is found to be much smaller than the amount of heat required to convert 1 mole of the liquid melt obtained into vapor at the boiling point, called enthalpy of vaporization, delta HVAP naught. For example, delta HF naught for ice is 6.1 kilojoule per mole, whereas delta HVAP naught for water is 40.7 kilojoule per mole. Greater the amount of heat absorbed, greater is the disorder introduced. Thank you for this session. So this was all about, this is not completing of the chapter. This is only a portion of the chapter. I will upload more audio clips, of course, audio visual clips for the next section of this chapter. So on. Thank you.